Over the previous chapters of general chemistry, you've learned about the possible products of a chemical reaction and the conditions of temperature and concentration that would determine whether that reaction proceeded spontaneously. Throughout those processes, however, we were never able to say anything about reaction rate. As we saw in the case of sugar decomposing into carbon dioxide and water, even exceptionally favorable processes are not necessarily going to proceed all that quickly. Now that we've reached Chapter 10, Reaction Pathways, we're finally ready to tackle reaction rate. To do that, I want to discuss an example problem. In this case, we're talking about the addition of phenolphthalein, a common indicator that you might have used in lab as part of an acid-base titration, to sodium hydroxide. At low pHs, phenolphthalein is colorless. However, when it's added to sodium hydroxide, it becomes bright pink. Now, in this example, adding the phenolphthalein causes it to immediately turn pink. I'm writing instantaneous. What I'm practically meaning here, though, is just really, really quickly. By comparison, the backwards process is slower. That is, in this reaction, the pink compound over time will react back. This is one of the reasons that when you were doing titrations in lab, you were told to measure your endpoint promptly once you found it. So this is the amount of time that we sought to measure. So I ran an experiment where we mixed phenolphthalein and sodium hydroxide under a set of varying conditions. In each case, the amount of phenolphthalein was kept constant, 1 drop, but we mixed it under various concentrations, comparing either 3 molar or 1.5 molar sodium hydroxide, and at an array of temperatures, 100, 25, or 0 degrees Celsius. Let's take a look at the experimental results that came from this. The 100 degrees C solution was observed to turn back to its original color in about 100 seconds. The 3 molar solution was observed to turn back to colorless in around 65 seconds. Our 25 degrees C and 1.5 molar solution was observed to recover in about 150 seconds. And last but not least, this cold example was observed to recover in about 300 seconds. What trends do you observe in this set of data? Well, one thing to observe is that changing the temperature or the concentration can change the reaction rate. That's probably a good thing to observe. Keep in mind that temperature and concentration were also the two things that we were changing when trying to shift spontaneity as well. What else do you observe in this data? Well, raising the temperature from 25 degrees C to 100 degrees C seemed to cause the reaction to go more quickly. This might agree with some of your own experiences in real life. Heating food will cause it to cook a whole lot more quickly than not heating it at all. Likewise, increasing the concentration caused the reaction to go more quickly. Last but not least, the opposite of that heating trend is also true. When we cooled the reaction down, it went more slowly. So it seems like reactions go more quickly at higher concentration and higher temperature. To describe that rate of reaction, we need again to get a little bit quantitative. We need to define reaction rate. Reaction rate is equal to the change in amount over the change in time. That change in amount might be a difference in concentration or in pressure, really anything that we can measure shifting in our reaction. And the change in time would be how long that shift took to happen. Thus, we'll wind up writing out rates that look like some change in whatever we're measuring, pressure in this case, divided by a change in time. In the next example, we're going to look at how this might be done for a particular problem.